Greetings, physicists. We are going to talk today about the center of mass, the idea of center of mass, or sometimes called the center of gravity, which I think there's a subtle difference between them, but we won't get into that today. So when we talk about center of mass, we're talking about objects. Whoops, let's draw here. We're talking about objects that have volume and are no longer considered point particles. Most of the earlier stages of physics, to simplify problems, if you have a crate sliding down a hill, you don't actually draw it that way. You draw it as a particle sliding down a hill because that makes the free body diagram easier, and it more or less acts like a particle. We will no longer be considering that model. We will now consider that this thing has one big shape, and there is mass all over it at different points. And what we're interested in is this idea of center of mass is going to talk about where do the forces act. So if I have this shape, and we'll assume that every little dot here plus all the dots in between that I'm not drawing, these are all points of mass. And the gravitational force actually pulls down on all of them at the same time. It's as if every single point of mass in this object is being accelerated downward. So there's an mg on that point, and there's an mg on that point, etc. And I could, essentially there's an infinite number of them in a continuous object. And what we do is we sort of sum them all up. That's the idea of the center of mass, to find out where's the average, more or less, of all of them. Now we're going to do this with, I'll make an easy example for you. Let's have a ruler. You don't actually need to do the math to figure out the center of mass on a ruler. You just need your finger. So if you were to slide your finger back and forth underneath the ruler and maybe find a point, let's say here, and the ruler balanced without tilting, you would have found the center of mass, or the center of gravity. Even though gravity is actually pulling down on every point of that ruler, because there's essentially, if you add them all up and take the average, the leftover essentially, is right there. And so if you press back up at that point, your force can exactly cancel out the gravitational force and the ruler will stay put. However, let's take the same ruler, and this time let's say that the center of gravity is probably about in the center because a ruler is a uniform object. Let's say you put your finger over here. Gravity is pulling down everywhere, right? There's gravity here and here and here. But we said this was the average. If you add that all up, it tends to act as if gravity were pulling down on that spot right there. You're going to push up on this spot right here. And look how that's going to cause a torque. In this case, a clockwise torque. So if you were to try and support an object versus gravity, at any place other than its center of gravity, the object will rotate. If you were to support the object at its center of gravity, the object will translate. You could push it upward or downward, but it wouldn't rotate. That's the idea of the center of gravity. And there's mass that we can use, or there's math that we can use to calculate it. So let's get into that. So I'm going to use this example. I'm going to have a dumbbell, but it's not going to be an even dumbbell. It's going to have a big weight, a big side and a small side. So we'll have this side as mass 1, and we'll have this side as mass 2, and we're going to connect them with a very thin piece of metal that is much lighter than both of the end pieces, and so that we'll say that the handle of this dumbbell, the mass is negligible. So we're ignoring it. Now, it should be intuitive to you if you've ever held an object that was not symmetrical, that the pivot point, if I'm going to find the center of gravity, it's going to be somewhere over here. It should be closer to the big mass, assuming these masses are even densities. So let's define some other things. From that pivot point to this mass, we'll call that radius 1. And from the pivot point to this mass, we'll call that radius 2. And so essentially, if this is balanced, if it's balanced on that pivot point, this point here is the center of gravity. We'll call that a position. That's the position of the center of gravity, or the center of mass. And each of these is producing a torque. The mass 1 is producing a torque in the counterclockwise direction, and the mass 2 is producing a torque in the clockwise direction. But they must be canceling each other out. So the sigma torque, the net torque, is going to be equal to, we'll call them torque 1 plus torque 2, and that has to add up to 0. And of course one of them would be negative. In this case, the second torque is in the clockwise direction, which is considered the negative direction. So if I'm really writing that, that's torque 1 minus torque 2, or the magnitude of torque 2 would be 0, or we could say that the magnitude of torque 1 is equal to the magnitude of torque 2. Well, we can also write this expression, and this is how we're going to get our center of mass equation. So what we'll do is, I'm gonna write out torque 1. Torque 1 should be equal to, if I go up here, or I guess drag that down, no, I want to go up. We've got a mass 1, and it's at a distance r1 from the center of mass. So its torque from the pivot point should be equal to radius 1 times mg, times the force, rf essentially. So r times mass 1 times g. And torque 2 should be equal to R2 mass 2g, like this. So let's look specifically at this distance. And what I'm going to do is I'm going to consider, gosh, I keep doing that. I'm going to consider that this axis here, there's like an x-axis going through here. And so we have, this is the position of the center of mass, and then the center of this, we'll consider this as like a particle. We could say that's x1, that's the position of the left-hand mass, and then the center of here would be the position of object 2. So, scroll, there we go. So if I write R1 in terms of that, and I'm going to make the positive direction this direction for position. So if I want the magnitude of R1, I simply take R1 equal to the position of the center of mass, and then I subtract out x1. That's kind of like the final minus the initial, yeah? And that would give me the magnitude of R1. If I do R2, I have to take the final here minus the initial if I want to get a positive number, and I would get x2 minus the position of the center of mass. That would be R2, if that makes sense to you. Hopefully it does. So when I plug those in, then I'm going to get torque 1 equal to x center of mass minus x1 times m1g, and then this would be x2 minus center of mass, oh gosh, I messed that up already, minus x center of mass, times m2g. Okay? And we know, essentially, that they have to add up to 0. Right? We know that torque 1 plus torque 2 has to equal 0. Well, that's going to have to mean, and again we have to make one of them negative. So I'm going to say that x center mass minus x1 times m1g. Come on, Kip. Subtract, if I subtract the other one, that should add up to 0. So I'm subtracting essentially this, which is x2 minus x center of mass, and then m2g. Okay, if I do that, that has to add up or subtract out to 0 if they have those magnitudes. And then we just solve this for center of mass, and that will give me an equation for the center of mass. So let's do that. Okay, how do I want to do this? Well, I probably want to distribute across my parentheses. Let's do that first. So 0 will be equal to x center of mass m1g minus x1 m1g, okay, minus x2 m2g plus x center of mass m2g. And that's just me distributing across the parentheses. And then I think what I'm going to do is I'm going to combine these center of mass terms. If I have x center of mass m1g plus x center of mass, oh, and before I go any further, notice there's a g in every term, so I'm just going to get rid of gravity here. That should save a lot of writing here. So equal to, I'm going to pull these out, I'm just going to rearrange x center mass m1 plus x center mass m2 minus x1 m1 minus x2 m2. Okay, hope that works for everybody. This is all still equal to 0. And let's do this. Let's go ahead and add x1 m1 and let's add x2 m2 to the other side. And since there's a 0 over there, they will just show up. So, oh, come on. x1 m1 plus x2 m2 equals the center of mass, the position of the center of mass, times m1 plus the position of the center of mass times m2. And I want this. So I'm going to factor it out. And I will get, so the left is not changing, I'm just factoring the right side to get x center of mass times m1 plus m2. And then I'm just going to divide by this. So what I will get my x center of mass by himself, and that should be equal to, on this side, I had x1 m1 plus x2 m2 on top over m1 plus m2. So you now have a formula for calculating where on any given object its center of mass is, because this x value is just position. Now, this works for any number of particles. I had done a dumbbell where I assumed that the left and right were basically like point particles, right? Big point particle, little point particle, pretend that's a straight line in between them, there. And then I can use those 2 point particles. If I assume that the bar itself doesn't have mass, I can say, where is this one? Where is that one? And I can put them in there. But this also works if you just had, like, add another rod and put another dude there, right? If you have more than one or more than 2 things, just do this. Plus position 3, mass 3, and then on the bottom you're going to add his mass in there. So it's position times mass for every object in your system divided by the sum of all the masses. That's it. You can do this in 2 dimensions too. And you can have an x center of mass and you can have a y center of mass, and it still works. So use that, because once you know where the center of mass is, that's where gravity acts. That's also the center of gravity. That's the point that if you want to keep this thing from rotating, if you were to hold it up, that's the point where you would want to push. And it's the point where they'll do problems like the hanging sign problems. Oh, come on. You've got a hanging sign. 8. It shows. And it's attached to a pole like this, and it's got a rope going out to there. Well, if that's a uniform sign, its center of mass is going to be somewhere here. So the place that gravity acts is pulling on here at this distance from the left, but the point where the tension acts is over here, which is at this distance from the left. So you'll get problems like this all the time. And if they gave you a rod with 3 masses on it, again attached to a hinge over here, something like this holding it up, right? You could compute the center of mass of this rod, maybe here, depending on what everything cost, and then you could solve the problem from there. But it's all based on that formula, which I, of course, dragged. Hey there. Oh my goodness. There, that formula, the one box right in front of you. Position times center, position times mass, add those up on top, and just add up the masses on bottom. All right, hope that wasn't too confusing.